And in this sequence, we will learn how to use exceptions in the OCaml programming language. Well, what are exceptions? OCaml provides exceptions which are useful for signaling and handling exceptional conditions, like in many other programming languages. But here, exceptions are just constructors of a special sum type written exn, but we all call it exception anyway. I mean, this constructor can have arguments like all other constructors, so it seems like just typical constructor of a sum type, like the one we have already discovered. But there are a few differences with respect to the typical constructor of traditional sum types. First one is that you can define new exception at any time. This is not the case for traditional sum types. So the sum type exception is somehow special. It can be extended dynamically when you need it. On the other side, there is also a limitation that comes with this extra power, the fact that the exception cannot be polymorphic. You must fix a type at the beginning. Well, to declare an exception, it's extremely simple in the system. You just use a keyword exception, like here in the top level we have written exception E, and we hit return, the system will answer just saying, okay, there is a new exception declared with a constructor E. And these are really just constructors. After the definition, we can just use, you see as here, we just can type capital E in this case. And this system says, yes, that's a value, capital E, of type exception, of the exception type. Well, once you have defined exception, the first thing you can do with this exception is to raise it. I mean, you can tell the system, I have found an exception, exception E, please stop everything and tell the word. Okay, to signal this exception, you use a raise keyword. So like here, raise E. The system answers now exception, colon, E, saying I have stopped the computation because I got an exception, this exception is E. And let me make it more clear, when an exception is raised, everything is immediately stopped, any computation, and we only get the exceptional value as a return. Like for example here, we are making a definition where you say, first we raise E in the expression that should return the list 1 and 2. Well, if we hit return, the system doesn't compute the list 1 and 2, doesn't return 1 and 2, but just stops with the exception E as soon as it sees. I mean, let's see this applied in a more realistic example. So let's say we want to define a head function that takes a list and gets the first element which is present in the list. Well, a natural definition could look like this. So we define the function head that takes a list. We define it by pattern matching. So if the list has at least an element, well, we return this first element. But what can we do if the list is empty? There is nothing to be returned. Well, this is a typical case where an exception comes in handy. So let's define an exception, empty list. Okay, so we choose a meaningful name, and if we are past an empty list, we just raise an exception, say this is an exceptional condition, empty list. Okay, well, let's see. So we pass a definition to the top level. We have defined our empty list exception. We define the function and okay, so now you see this function is accepted by compiler that say you have a head function, take an alpha list, return an alpha, but actually in one particular case it will raise an exception. Let's test it a bit. So we can say, for example, head of the list 1, taking 1, 2, 3. Of course we get 1, which is fine, and if we call a head function with an empty list, well, as you might expect, we get an exception now. I mean, this is an exception saying, well, we couldn't find a meaningful result to return. We have an exceptional situation. What you get back is an exception. Well, it's very interesting to be able to raise exceptions, but it is also fundamental to be able to capture them and do something with them in case you want to handle exceptional situation. This is done in the OCaml programming language with a try with construct. Here we have an example of the syntax. So basically you write try then any expression you want, then with, and then you have a pattern matching. What happens? Well, basically the expression E is evaluated. If it doesn't raise any exception, fantastic. The result of the try with construct is just a result of E. But if an exception, let's say capital E, is raised, then this exception is matched with all the patterns that come after the with clause. And here you can, it is just general pattern matching, you can use any legal pattern. If this exception matches some pattern, let's see pattern I, then the result of overall construct will be the result of evaluating the expression EI. Now, be careful, all of the EI must have the same type and must have the same type as E, because these are all the values we return in the exceptional situations in place of the result of E, of course. Now, so let's consider an interesting question. Let's take a list, possibly a long list of integers. We want to multiply all the elements in this list and do it efficiently. So we have already seen solutions to this problem, but now we are considering a corner case which is interesting. What happens when inside the list we find the number 0? So as soon as we find the number 0, we know that there is no point in continuing the evaluation of the rest of the list. The end result will be 0. So a straightforward way of implementing this remark is a definition like this one. You see, we are defining our recursive function multl for multiplication of a list that returns 1 on the empty list, and when the list is not empty, it checks whether there is a 0 at the beginning. In that case, it just stops the computation and returns a 0. And otherwise, it calls it recursively on the rest and does a multiplication by a. Okay, this is a definition that works perfectly well. We can try it on an example. For example, this one. Okay, of course the result is 0. Here we have find this 0 in the middle. But the point is that this is not as efficient as it seems, because indeed, as soon as a 0 is found in the list, for example in this position here, what happens is that one gives back as a result a 0, but then all the pending recursive calls have to be executed, and this will end up making a lot of multiplication of the 0 that we have as the result for the elements which are pending there. So it can take a lot of time. Imagine you have a 1 million integers and you will find the 0 just at the end. You will need to make 1 million multiplication by 0 by coming back. So is it possible to be faster than that? Yes, and this is a typical situation where having exceptions can save you a lot of computation time. So let's redo the previous example, but now use an exception to stop the computation really, without coming back to recursive calls, instead of just returning 0. How can this be? So we define an exception, 0, it's a meaningful name, and then we define our multiplication of list with exception, this function here, in a different way. What we want to do is to do a computation like the previous one that will raise a 0 exception as soon as a 0 integer is found, then catch the 0 exception and return 0 as an integer as a result. So definition of this internal function, auxiliary function, is similar to the previous one. The only point is that as soon as we find a 0, we raise an exception. We raise exception 0 here. This will have as a net effect of throwing away all the recursive call stack and just raise a final exception 0 to the caller. Yeah, so we can pass this to the interpreter and see what is going on. Okay. So we can test it is accepted again, and again exception, we can test it on a similar example. We also get 0, but believe me, this time it was much faster because we have thrown away the call stack. We have seen how to create new exceptions, how to raise them, how to handle them. But it is very interesting to know that in the OCaml system, many runtime errors are also catched as exception and returned to you as exception that you can manipulate. Well, you remember, in OCaml, the type errors are catched at compile time, but there are many other errors which are not type errors. They cannot be catched at compile time. Okay, so these are runtime errors. Typically, divisions by zero, incomplete pattern matching, out-of-bound access to mutable data structures, and many others. What is very nice is that in OCaml, when these errors occur, your program does not crash. What happens is that the system wraps this error into an exception which is raised, and then this exception is something that you can handle. Let's see this on some examples. Okay, so let's try to see what happens if we make a division by 0. For example, let's divide 3 by 0. Well, of course, we get an error. The system says that an exception was raised, which is actually named division by 0. And this is really the constructor of the exception type, which is named division by 0. Other examples, let's try to make an out-of-bound access to a mutable data structure, for example, an array. Here we define an array with 3 elements. We see here, first element is 1, second is 2, a third is 3. But now you remember arrays in OCaml starts from 0, as it happens in other languages. So if I access the first element, it's actually v of 0. But imagine that sometime in your program you forget that you are starting from 0, and you try to access the third element by using v.3 instead of v.2. In that case, well, we get another exception, which is an out-of-bound error from the array. But in this case, you see, instead of crashing the program, as it can happen in other languages, you get just the runtime error wrapped into an exception that you can capture and you can manipulate. And this is an invalid argument index out of bounds actually tells you that at runtime there is a write bound check which is performed for you by the system. The third case we want to show is what happens if you decide to ignore the recommendation of the compiler. Like, for example, in this definition of function here, it is clear at this point in the course that the pattern matching is not complete because we are not handling the case of the empty list. This is just a drop function that takes a list, drops the first element and gives you the rest. But what happens if you have an empty list? There is nothing to drop. And we didn't say what is going to happen. So the compiler, if we send this function definition to it, finds that the pattern matching is not complete, and actually the example value which is not matched is exactly the empty list. Yeah. Anyway, we can bypass or ignore this warning, and the function is still defined here. We can try to use it as it is. Of course, as long as we use it on a non-empty list, everything works. But when we are trying it on the single case on which the function definition was not perfectly done, we get an error, which is a match failure exception. So at runtime, there is a case which was not contemplated in the pattern matching definition. But again, the program doesn't crash, it only raises an exception that we can catch and handle later on. To sum up, we have seen how exceptions work. They are constructor of a special exception, some type which is extensible. They can be declared and raised using a very simple to remember keyword, just exception and raise. You can handle and capture exception using the try with construct. And they are very useful for signaling and handling exception condition, for altering flow control, for writing more efficient algorithm. And what is really good to know is that unlike what happens in other programming languages, raising, handling exception is extremely fast. So please use them if they fit your algorithm.